Welcome to The Explainer. In this one, we're going to break down a really big topic into something you can actually wrap your head around. We're talking about the invisible force that powers, well, pretty much everything in our modern world, electromagnetism.
Okay, so let's just jump right in. You see these things everywhere, right? Electric cars. We know they have huge batteries, but how does that stored electricity actually make the wheels turn? I mean, really, think about it. How does a flow of tiny little electrons create enough force to move a whole car? That's the puzzle we're going to solve today.
So let's talk about where this all began. Our story kicks off way back in 1820 with a discovery that honestly changed everything. So this guy, Hans Christian Ørsted, is in the middle of a lecture, and he's got a wire and a battery. And just by chance, there's a compass sitting nearby. Every time he connected the circuit and current flowed through the wire, he saw the compass needle twitch. Instead of pointing north, it just jumped sideways. It was a total accident. But what he discovered was huge. Electricity and motion creates a magnetic field.
Okay, so now we know there's this invisible magnetic field, but how can we predict it? Let's check it out.
Right, so a current creates a magnetic field, but which way does it go? Does it just swirl around randomly? No way, this is physics. There's always a pattern. And luckily for us, there's a super simple trick to figure it out.
And here it is. It's called the right-hand grip rule, and it's awesome. Seriously, do this with me. Take your right hand. Imagine the wire is right in front of you. Point your thumb in the direction the current is flowing. Now, look at how your fingers naturally curl around. That is the direction of the magnetic field. It's a perfect little built-in cheat sheet.
So let's see this in action. Look at the left image. That little dot in the middle, think of it like the tip of an arrow coming straight out of the screen, right at you. So point your right thumb towards your face. See? Your fingers curl anti-clockwise. Now look at the right. The X is like the feathers on the back of the arrow flying away from you into the screen. Point your thumb away from you. Boom, your fingers curl clockwise. It's that simple. Reverse the current, you reverse the field. Period.
Okay, that rule is pretty cool, but what's it good for? Well, this is where we turn a simple wire into a real workhorse, the electromagnet. So instead of just a straight wire, what if we wrap it into a coil, like a spring? This shape is called a solenoid. And here's the magic. The little magnetic field from each individual loop of wire all add up. It's like a team of tiny magnets all working together. The result? You get a really strong, really uniform magnetic field right down the middle that looks and acts just like a regular old bar magnet.
And the best part is, we can totally control how strong it is. It's like a recipe for a super magnet. Want to make it stronger? Option 1, pump more current through it. Option 2, just add more turns to your coil. Or Option 3, and this is a really clever trick, stick a piece of iron, what we call a soft iron core, right inside. That core basically acts like a superhighway for the magnetic field, concentrating it and making the whole thing way, way more powerful.
Okay, so a magnet you can turn on and off. Where would you actually use that? I mean, besides the obvious giant scrapyard crane thing. It turns out this on-off ability isn't just a cool party trick. It's a life-saving feature you probably have in your own house. It's inside your circuit breaker. So here's how it works. Normally, you've got a steady current flowing through that little electromagnet. It's on, but it's pretty weak, not strong enough to do anything. But let's say there's a power surge. Suddenly, a huge amount of current rushes through. That weak electromagnet instantly becomes a supermagnet. It's strong enough to pull that little metal plunger, which flips a switch, and bam! The circuit is broken, the electricity is cut off. It all happens in a split second, and it literally just saved your house from a potential fire.
All right, so we've got electricity making magnets. Now, let's mix things up. We're going to see what happens when these forces collide.
So really think about this. We have our wire with current flowing through it, right? And we know it has its own little magnetic field swirling around it. Now what if we take that whole setup and stick it inside a different, bigger magnetic field, like between the north and south poles of some big magnets? Now you have two magnetic fields in the same space, and they are absolutely going to interact. They're going to push and pull on each other. And this is what that interaction looks like. See the straight field lines from the big magnet? Now look at the circular field lines from our wire. Above the wire, the fields are pointing in the same direction, so they team up and get stronger. Below the wire, they're going in opposite directions, so they kind of cancel each other out and get weaker. Well, physics doesn't like that imbalance. The wire gets pushed from the strong area into the weak area. It literally gets a physical shove. This is the motor effect. So, of course, there's a rule for this too.
We need to predict which way the wire is going to get pushed. For this one, you're going to need your other hand. It's time for Fleming's left-hand rule. Okay, get your left hand ready. Make your thumb, forefinger, and second finger all stick out at right angles to each other, kind of like a 3D axis. Now here's the trick to remember it. Your forefinger is for the field, your second finger is for the current, and your thumb gives you the resulting motion. So think field, current, motion. Use your fingers to point in the direction of the first two, and your thumb will show you exactly where the force is going. Okay, we have all the ingredients. Let's put it all together and see how we build an actual electric motor. And this is it, the blueprint for a simple DC motor. It's got everything we've just talked about. You can see the big permanent magnets creating the field, and right in the middle, there's a coil of wire just waiting for some current. Let's make this thing spin.
Okay, let's use our new rule. Look at the left side of that coil. The current is flowing into the page. The magnetic field is going from north to south, so from left to right. Get your left hand out. Point your first finger to the right for the field. Point your second finger into the screen for the current. Where's your thumb pointing? Up. So that side of the coil gets pushed up. Now the other side. Current's coming out. First finger still points right, but now your second finger points at you. Your thumb is pointing down. So one side goes up, the other side goes down, and the whole thing starts to turn.
But hang on, there's a problem. Once the coil flips over halfway, the side that was being pushed up is now on the side that gets pushed down. It would just flop back and forth. This is where the real genius comes in. See that little copper ring with the gap in it? That's called a split ring commutator. Its only job is to cleverly reverse the direction of the current flowing into the coil every single half turn. By flipping the current's direction at just the right moment, it makes sure the force on one side is always up and the force on the other is always down. And that's how you get a constant spinning motion. And that right there is the whole story. It's just two simple rules. 1, electric currents make magnetic fields. 2, magnetic fields push on electric currents. From those two ideas, you get blenders, fans, power drills, and yeah, you get the giant motors that turn the wheels of that electric car we started with. It's all the same principle, just scaled up. So, the big takeaway here is that some of the most complex things we use every day are built on a couple of surprisingly simple, elegant rules. This motor effect is happening all around you, hidden inside dozens of devices. So the next time your phone vibrates or you turn on a fan, you'll know the secret. The real question is, where else are you going to notice it working?